Welcome to TypeScript tutorial 0 to Hero. We are diving into the second part of our tutorial series. If you haven't watched the first part and wish to grasp the basics of TypeScript, you can find the link to the previous video in the description below. In the second part, we'll focus on patterns that enhance the maintainability of our codebase. Our journey begins with understanding type narrowing, followed by a quick overview of type predicates. Then, we'll explore built-in utilities that offer flexibility during refactoring and creating new types from the existing ones. Next, we'll learn about templates, which enable the representation of abstract type families. These templates will play a significant role in the generic functions, which are an essential component of every complex TypeScript application. A proper implementation will ensure a smooth developer experience when implementing new features. Wrapping up this segment, we'll dive into the basics of classes. You can find a link to the interactive roadmap, code examples, and transcript of this video in the description below. Working with basic types and managing them within a codebase is relatively straightforward. However, challenges arise when dealing with unions of different types. There are certain techniques that can simplify type detection, which will be the primary focus of this chapter. Narrowing down a union type or broader types like any or unknown to a primitive is easy. The JavaScript type of operator helps in accomplishing this. Here we have an example how to detect safely string, number, or a boolean. Using strict equality helps in checking for specific values. This is useful for detecting specific values within a union type, as well as null and undefined. On the screen, you can see how we can detect null or undefined. Strict equality will also help when we want to check for a specific value. For example, here we have a function that can only accept two specific strings. After the check, we can safely execute the function. There are two ways to check for undefined. In TypeScript, using modern ES syntax, TypeScript itself checks for variable existence, so we can safely use the strict equality approach. The usage of type of x equals undefined handles undefined global variables. This check is useful for global variables like window inside server-side rendering. However, when checking function arguments or declared variables, relying on equals undefined is preferable. To determine whether a variable is an array, we can use the built-in utility array. Naturally, this will only check if the variable is an array. It won't provide any information about the shape of the items. Detecting an object is a complex topic. Let's begin with the basic and naive approach. For general object detection, we can use the type of operator and simultaneously check if the value is not null. If you are wondering why we need this extra check, type of null equals object. JavaScript, as always, amuses its users. This check isn't useful in most situations. It would be much easier to begin by checking for other types of variables and eventually identify the object type. We start by checking for a string. TypeScript understands that what's left includes our object and null. After checking for null, the last option remaining is our object. Now we can safely access the name key. We've learned how to detect an object type in a union containing basic types and one object type. However, there is a challenge in differentiating between multiple object types. Sometimes we can safely execute the code by checking the type of specific keys. However, as you can see in the example, it doesn't narrow down the entire object type. Checking for the existence of the key is not a viable option. The challenge arises from the duck typing concept fundamental to this language. Because TypeScript only verifies if the object type matches the general interface, we cannot depend on the absence of properties. In the example, we have a union that can accept an object with x string or an object with y number. we create a function that should always return a string. We check for the existence of the X key and adjust our codebase based on the A or B type. Initially, basic test seems to work fine. However, when we create an object that matches our required union, but also contains the X key of a different type, we receive an invalid output. On the example, it's a number. The code becomes unsafe, and TypeScript will not issue a warning. Lessons learned. Let's not rely on the existence of the key to determine the object shape in our codebase. The solution to detecting a specific object's shape involves introducing a guard property within the union of types. This property allows us to precisely define the type of the variable. As a guard, we can choose any property, but it is often a key like type, guard, kind, etc. We typically base it on the types of the objects. After checking for this guard type in an if statement, we can be certain about the proper shape of the object. The guard can take multiple types. It should clearly define which object type we are working with after the check. In the first example, we are using string guards inside the kind key. This key is specific to each of the types, so after checking its value, TypeScript will know which type are we dealing with. For instance, when we check for the kind to be basic, we can access the date, score, and text keys. The same applies to checks for tech and global guard values. The guard doesn't necessarily need to be a string. We can also use numbers. In the example on the screen, we can observe that when using guards, narrowing still works. Therefore, after checking for one type, the other branches will only consider the types that remain. The next example showcases the usage of enums as a type guard. The rules are the same as shown previously. In the earlier part of the tutorial, I shared my personal opinion about the usage of enums. The last example of the type guard is an alternative where we can use asconst object and its values to facilitate object type detection. I frequently use this pattern in my personal projects. Pay attention to how we define the type of the guard key inside type definition. Since it's not an enum, we must use the typeof keyword to utilize the key's values as a type. The rest remains the same as in the enums example. Class detection can be achieved using the instance of operator. Avoid relying on checking properties or methods, as the same rules applies as was shown for using the in operator for objects. In the example, you can see that after checking the argument inside the if statement with the instance of operator, TypeScript identifies the kind of class instance we are dealing with. When using with inheritance, the same rules apply. Hello, as in the first part of the tutorial, after the theoretical part, we will go through the code exercises, and let's start with type detection exercises. So the first one is an exercise on the primitives and their detection and the if statements. So we have the value that is unknown, this is coming from the local storage, and we want to check for in the first if statement if it's a string. So we can execute, for example, to uppercase safely. So we are gonna go for type of operator, and for the strings it will be checking for the equality to the string. So now we can call the to uppercase safely. In the next line we have the numbers, so we're gonna do the same. We're gonna go for type of operator, the value, and check for the number. Now we can call it to fixed. And in the last one we're gonna go for the boolean check. So we're gonna go for type of value equals boolean. And this is how we can safely handle checking for the primitives. The next example is about the strict equality checks that can help us. So we have the defined variable, which is also like unknown. And let's start with the going for the null. So as I said, the easiest way is simply to check for the null inside if statement. Then we can be sure that the value is a null. Also, as I said, the value is a defined variable, so we don't need to go for the type of value equals undefined. Here we can go simply for the strict check, value equals undefined. We know the value is undefined. Okay, so we have also the function that requires two specific strings, not the general string. So let's comment this out because this is not a valid check, but the get and post strings. In the TypeScript, when we check for the specific values, the TypeScript will understand that these values are what is left after the check. So if we go for the value, it knows now it's either a get or post after this check. So now we can safely call isValidRequest. So this is how we should approach this kind of checks when we need like specific strings. Okay. The third example is about the handling of the global variable. As you see, we have the problem because TypeScript is complaining that he doesn't know that there is like some kind of global variable. For this, I will uncomment this prepared line, which is like only telling the TypeScript there is like a global variable existing. And as we were discussing, if we are going for the global variables and we want to be like double sure that is our check will be fine, we will go for other check, then strict equality to the undefined. We're gonna go for type of global variable is not undefined. And now this is like much safer because even if the variable would not be defined inside the global scope, the code will not crash. This is like but as I said, go for it only for the global variables. If we have a local variable, then this variable is gonna be defined. So this simple check with the undefined will be enough for us. Okay, the fourth example is about the handling of two different types of the input. So we have the function that is accepting an array of the strings or number and should return a string. Okay, so we have the general idea that when we have the array, we want to join the strings or return the number to fixed if it's the number. So we're gonna do it in two ways. So first of all, we're gonna check for the number. So type of x equals number. If we have this check done, then we can simply call to fixed because we know it's a number. And what is left is an array, so it will be x. On array, we can call join function. We can do it like another way. So we can start with checking for the array. So it will be using array is array x. So okay, now we know it's an array, so we can call the join method. And after the check, we know that what's left is a standard number, so we can call to fixed. To be honest, I have no preferences which one is better because we have only two things to check. So whatever you choose, it will be fine for this part of the code. The next example, we have a complex input that has number, null is optional, so undefined, and the object. So we want to access the age of the author or return the age, author as an age. So as I said, when I have this complex list of types in the union, I will go for the easiest types at the start. So I will check for the null and undefined, because undefined is also an option here. And if we have these two, I will simply return, because to be honest, I cannot really deal with this kind of data in this function. So what's left is the object and the number. As I said, it's easier to start with the number, like a primitive, because the check is much easier. So we'll go for if author, type of author equals number. Oh, okay, I messed off. Type of number equals number. So then I can like console log author, because we know it's like a number. As you can see, the TypeScript knows it's a number. Or in the else statement, we know what's left, that the author here is the object. So we can simply go for console log author h. And as I said, I would go for the easiest type detection first and leave the objects at the end if I need to. Of course, there is the alternative way. If we have this union that contains only one object type, we can go for statement like if type of author equals object. And as you probably remember, we need to check if the author is not a null. And now after this check here, we would be also like safely to access the object structure. As I said, maybe it's easier to start with the easiest primitives. Okay. In the next example, we need to handle safely different object types. Okay, so we have the function that we can pass the list of the authors and the title of the book, and we want to find the author which contains the book that matches the past title. So let's start with the looking for the author. So I'm gonna look for the author inside the author list. So we're gonna use the find method. As you can see, when I'm using the find, the TypeScript is helping us what kind of type of the item is expected inside the array. So it's author or undefined author. But we are looking for the books. So the books are having the same shape inside the author. So the books, and we're gonna need to find if there is a book of this title. So here will be some book. And as you see here, we have also type helping. We know that the book contains the title. So we're gonna look for the book that titles equals title passed in the argument. Okay, so what we have after this operation, we found the author that has the book that title is matching. And the output is an author, a non-author, or undefined. So let's go for the first like eliminate us not finding author. And for this, we return unknown. Okay, so what is left is now that we have like author and undefined author. In this case, we have like a string that is a null, or the string, the name this is which is a null or a string. So this check will enable us to find the unknown author type. So if we check if the author name equals null, that we know this is unknown author. So we can return unknown as well here. So after elimination of the unknown type, we can simply return here the author will be, as you can see, author will be f-type author. So we can return a string template which will contain the author name and author surname. Okay. Yeah. Of course, we can make this code a little bit better, so we don't need to have this like two checks. Simply like this, it will be enough for us. Okay. So the next example is showing and forcing us to understand the problem of using in check to eliminate different types of objects. So this is the example that is checking if we are having y key inside past object to the getResult function. If it's so, it's handled like an array. If it's not, it's handled like a string. So for the first example, we are passing x, so there's no y, we return x. So it will be a value. For the second example, we have an array, so y is inside the input, and we are joining the array. So the response is easy. It will be like joined string. For the third one, this is start to be like a little bit challenging because we go to the first branch. We could, like, all of the branches are fine, but we go to the first branch of the logic. So we're gonna return value, not the example. And the fourth one, we have the Y key. So we go into this part of the code. The TypeScript is not complaining because X is following the type A, but in our code, we're going to the Y inside the input and treating it like an array. So this is an error for us. That's why let's not use the in check for the types of the objects. The better approach, of course, to handle different type of the objects is using the guards. And this example is about introducing a guard into our types. So we have like three different types of achievements, and I'm gonna create a kind, which I'm gonna use the easiest guard to implement for quick demonstration. So the string guard. So we're gonna have like the recurring kind. In the unique, we're gonna create unique kind key. And for the legendary, we're gonna go for legendary. And now, when we are having this kind of general achievement passed to our function, we can go for these checks to be safe and to know exactly which kind of achievement we are working with. So if achievement kind equals, and let's start with legendary. Sorry. Okay. So now I can access all of the types that are in the legendary. Let's go for the title and event. Yeah, so let's return some kind of basic string template that will display anything. Simply, we are not really caring about what we're gonna return from this function. The main goal is to go for the type guard checks. So now what is left, the TypeScript knows that we eliminated the legendary type. So we're gonna for, let's say, recurring. And then again, I can extract the even, like the achievement. I can go like for date, let's say, and return date to is a string. And TypeScript knows that what is left is the achievement of the unique type. So when we go for the achievement, and we would like extract to here, it will be like description place. And yeah, let's return this one. Yeah, place. So as you can see, working with type guards really helps us to handle multiple different object types. It would be a nightmare to trying to deduce, okay, if the title is a string, if the date is a date or an array of the dates, it would be a nightmare for us to work with this. Now the code looks much cleaner. We can like extract these parts to the separate functions. Will not mess up this code. This is really good solution if you have like different types of the objects. I really encourage you to use this kind of pattern inside your applications. Okay, and the last example is about the detection of the specific class instances. So we have the input that is either a date or some kind of object. So this is like the example for detecting of the instance. So we're gonna use the instance of operator. So we are checking if the input is the date. If it's a date, let's return to isostring. And here, after checking for the date, we are safely to assume that the input is an object, which will contain only like this day, month, and year fields, and we can return. Yeah, let's return some kind of. It will be not refined, just a simple solution. Of course, it's not perfect because we would need to add zeros to have the nice display of the date. Yeah, but this example was, the main idea for this example was to check for the instance of the date. Okay, so we're done with the exercise with the type detection. The next part of the tutorial will be focusing on the type predicate. In the previous chapter, we explored methods to write checks within our code, enabling TypeScript to safely detect and automatically narrow down the type of a variable. Additionally, there is a specific approach to create a function that informs TypeScript about the variable's specific type. This is known as type predicate. Let's create a specific type guard function that, when it returns true, marks a variable within the code branch as a specific type of value. Let's illustrate this with an example. We have types called dog and parrot, and their union forms a general pet type. We create a function isDog that receives a pet. If the function returns true, it signifies that the passed variable is of type dog. Observe how we define the return type of such a function. The is keyword is used specially for this type predicates. Upon checking the variable, we can utilize the bark method. TypeScript acknowledges that within the if statement, it's safe to handle my pet as a dog. The narrowing process remains functional. In the else branch, we recognize that the remain type will be parrot. These functions can be incredibly useful when combined with utility functions like array filter. Let's see how it works. In the standard filter function, when we create a valid function to limit types to dogs, the outcome will still be an array of pets. We could cast it using as, but there is another approach. Let's provide a filter function that serves as a type predicate. We define it to return whether the item is a dog. After filtering, we obtain an array of dogs. This is much better because now we can safely and more precisely handle the items that remain. Of course, we can define this filter as a separate function, as was shown in the previous slides, and then use it inside the filter method. This would result in even cleaner code. However, there is one caveat regarding type predicates. When we designate that the variable is of a specific type, TypeScript trusts us, similarly to what happens with as keyword. That means we can make mistakes and introduce bugs into our codebase. In the example, we have the isDog function, which is implemented in an invalid way. The check is not proper, but after usage, TypeScript doesn't show any errors. This can result in our code behaving improperly. The absence of a proper check implies that during refactoring, such functions should be also validated. As you notice, the type predicate has a unique syntax. We can also create a type that represents a type predicate. The syntax is visible on the screen. One small note. For the example above, it doesn't really make sense to ask for a predicate filter for a known type. This is purely for illustrative purposes. Often, the predicate type is used as the type of a function's argument in generics. We will revisit this topic soon. Now we are ready to go through type predicate exercises. We have two of them, but I think they will cover the topic that we are talking about. So the first one is about having this code executed safely. So we have the items, which is an array of 20 randomly generated strings or nulls, and we want to have it filtered so we can use toUpperCase method. So here, like from the JavaScript at least perspective, the good solution would be, okay, we have the item, we want to have the item, it's not null, and this code would work fine, but for TypeScript, the X is still a string or null, so we need to use the type predicate here. So after this check, I'm gonna mark that the item is a string. And after this, now the TypeScript knows that, okay, after filtering, what's left is only strings, so our code is now safe, no warnings, exercise first is done. And the second exercise is about defining the predicate function. And we have dog and parrot objects, and we want to have the isDog function that is used to filter out the randomly generated pets to have only dogs there. So first of all, I'm gonna mark what this function is all about. So it's all about checking if pet is dog. And how we can do it. Okay, we know that the bark method is unique to the dog, and we could go for this check. So it will be like bark in pet. And for this kind of logic that we have here, it would work fine. But as I said in the previous examples, that this check is unfortunately not the best one. So what would be the great for us would be to simply add some kind of like type guard for the dog and parrot types. And now after adding it, of course, I'm gonna need to fix the randomly generated function to have the proper objects returned. So we're gonna meet this, and for this it will be a parrot. And now we can simply have here pet kind equals dog. Now this code cannot go wrong even if we try really hard. So yeah, we were focusing here about like marking the variables to be a specific type using type predicates, and also maybe fix a little bit our code introducing type guards. The next examples will be about the utility types, and let's go to the theoretical part first. In various parts of our code, we may require a type similar to an existing one, but with slight modifications. We could opt for copying and pasting the existing type and making necessary alterations where required. However, this approach becomes cumbersome when we intend to update our type system with new changes, as we would need to modify each dependent place. Utilizing built-in utilities can significantly reduce boilerplate and establish relationships between dependent types. This, in turn, enhances the safety of our codebase and streamlines the refactoring process. We will begin by exploring utilities that allow object type manipulation. The partial utility makes all values optional. This utility type is frequently used, for instance, to define the type of a configuration object containing default values that users can override if necessary. In the example, we have a handle file download function with the config parameter, which users can partially pass. Note how we assign an empty object as the default value of the config. When checking for the values of config keys within the function body, TypeScript will indicate that the value can either match the definition in the save file config type or be optional, undefined. Required is the opposite of partial. It generates a new type that eliminates the option to skip a key or assign an undefined value. This utility is valuable when we aim to enforce the passing of all required data. In the example, we have form state type where all keys are optional. Consider a scenario where we have a function to submit the form, requiring all data from the same form to be present. We can specify that this function's data argument must be of type form state, but with all fields required. The read-only utility marks every key and its value as read-only. Let's consider a scenario where we have a config object that should not be modified. We can mark its keys as read-only, and TypeScript will perform static code analysis to ensure that we do not change these values. In various situations, we can often require specific parts of objects. Depending on the scenario, we can use two methods to extract only the necessary fragments. The pick utility enables the extraction of a list of keys along with their corresponding value types. The first argument is the object type, and the second is a union of keys to be picked. The example showcases the author type. We need only a part of it, the name and surname. We can use pick to create a new type from author and develop a function that requires only parts of the object. Imagine that we want to use the function with only partial data, for example, without fetching books. Having a less strict input makes the function more flexible, as it does not require as much data as with the original type. Conversely, omit works by specifying the keys to be excluded from the resulting object type. We create the author without books type by using omit. The syntax is similar to pick. As the first argument, we pass the object type, and the second argument is a union of keys to be removed. Of course, we are able to pass only one key if needed, as in the example. As you probably noticed, both utilities can return the same result type, as illustrated below. We can use pick and list the keys we want to be included in the final object type, or we can use omit and remove unnecessary keys. Choosing the appropriate utility will depend on the context where the reduced object type is being used. Utilize pick when specific keys are expected, such as in the helper function requiring only particular keys. On the other hand, when employing the object destruction and using rest property, omit is recommended. Furthermore, omit can be useful in the situations where a part of the object needs to be removed before proceeding with the subsequent code. Why should we care about using the proper utility if the resulting fragment type is the same? Making these considerations allows us to foresee potential changes and limits modifications for the pick and omit second arguments accordingly. This proactive approach ensures type checking accuracy, ultimately reducing the time required during refactoring or implementation of new features. TypeScript provides built-in utilities that can extract parameters and return types from the provided function type. When we use parameters on the function type, the result will be a tuple whose indices cover arguments of the function. As always, if we want to extract the type of an existing function, we need to use the typeOf keyword. In the example, if we wanted to extract the type of the first argument, we would use params0 to do so. Return type is easier. It returns the type of the result returned by the function. In the example, it's a promise that resolves to an object with XX and YY keys. These utilities are not used as often as object utilities, but sometimes we want to have compatible return types between functions, and we can use those types to enforce such behavior. The following code example will be familiar to Redux users. We can extract the state of the store using return type on the store getState function. Imagine that we add a new reducer to the store. TypeScript will automatically recognize that there is a new key inside the store states. Everything is updated without any need to change in our type system. Then we can use this return type to create type-safe things, or more specifically for React, create a custom useSelector hook. Personally, I sometimes combine parameters and return type when writing unit tests for functions. This is useful when I want to test multiple arguments and results simultaneously. When I use parameters and return type, I get an additional check if the tests match the expected arguments and result types. There are also utilities that make working with unions easier. Exclude allows removing specific values from the union type. In the given example, we have a union of verification status type. In a certain section of the code, we can manage every type of status except already verified. We can create a type from this union based on the original verification status, but exclude already verified. The syntax of the exclude utility involves two arguments. The first is the original union, and the second is another union whose values we aim to exclude from the first one. You can perceive this operation as a set subtraction. The extract utility limits union values to a list of specified possible values. It will be visible on the subsequent example. Here, extract A, B results in a union containing only C and D strings. This operation is an equivalent of set intersection. While intersection might be considered to be the same mechanism, it's not. The usage of extract forces logic to look at the arguments as union. The difference becomes noticeable when dealing with object types. The intersection of type A and B is a combined object, while extract produces never. The extract operator looks on the object as a union of one type. The A and B unions do not have any common type, so the result type is never. Additionally, there is non-nullable, which excludes null and undefined from a past union. This is the same as using exclude with null undefined union as second argument. Choose one that feels more natural for you. Utility types make our codebase much more flexible in the future and easier to refactor, so let's go through the exercises now. The first one is making the code work better for us, so let's go and analyze the setup. We have the achievement type and we have the save achievement method, and we would like to modify the create achievement function so it can be called with proper, with this kind of setup that we have here. So as we can see, we can pass only parts of the achievement data, and rest of them will be provided from the standard values. And this is the example that is designed to show the usage of the partial utility type. So let's start with this one. So we have the achievement and we have like the default values. So here when we are passing data, we don't really need to pass all of the keys. So we need only the partial part of the achievement. And to make this work fine for this empty call, we need to have some kind of default values, which will be an empty object, which is a valid partial type of the achievement. And with this way, we created a function that we call, it's super easy for us to use it properly because the TypeScript is really helping us. What kind of things that we can pass? Okay, we have optional date, description, title, type. It's super nice to use. And this is where we can use this partial utility just to have some kind of configuration that is optional while we are still working with the final type that is strictly defined. The second example is having a little bit more complex logic for this create achievement function and save achievement functions. And we have this kind of rules. So the save achievement should not take date and ID, but return it after the creation. So these parts we should be not passing to our code. And we want to create the achievement, so we need to provide description and title. Okay, let's focus on these two parts. We'll make it promise at the end. So first, let's define what will be the outcome of save achievement. For now, it will be an achievement for us. But what kind of input data are we expecting the user to pass? So let's start maybe with that we should not take date and input. It will be a little bit longer type, so I can move it to the new line. So we need to skip this kind of parts of the object. So we'll start with omit. And we want to omit both ID and date. Okay, so now we have this one. And let's start our implementation step by step. So we're gonna return, and let's return our achievement that is passed as the argument. Okay, so we have the problem because TypeScript knows, okay, we are missing ID and date. This is what we wanted. This is how we define it. So ID, I'm gonna return a random ID. It's not a really random ID, but let's say this is some kind of function that it creates a random ID, and the date will be also new date. As I said, whatever we have here. Okay, so the save achievement now is working properly, but we have this also rule that we should require only description and title, not other parts. Okay, so Other parts can be made optional. So let's go with optional. That would be the optional, but now we are missing some kind of data because type is optional and stuff like this. So let's go and pick what is the required parts, because we're gonna pick the required parts and leave everything else to be optional. So even like we have the duplicate keys, for example, for required description and title, the final outcome of the intersection will be the required description title, and rest of the parts will be optional. So here the TypeScript now says that the property type is incompatible because it needs some kind of default value. So the type by the default, it will be standard. Yeah, so why did I go for the pick and omit and with partial? Let's say we will create some kind of new field, which will be a string. Now we need to only define new field default value, and the types are now adjusted by itself. So we only need to provide new property if we would like go to the picking of the partial of the, let's say, type. We would probably skip or miss that we have a new field inside codebase. So just thinking forward, we can like specify exactly how the function should work and force us to have that like automatically updated in the future. Okay, so let's go to the third part. We wanted to make our function working as a promise. So I'm gonna return the promise resolve object. And of course we need to fix our function because now it should be an async function probably, and it should return a promise of the achievement. Okay, and when we are creating achievement, let's say we don't want to because okay, what we could do, we can copy and paste it. It should work fine. But let's say we want to reuse the save achievement input type. So here what we can use, it will be the parameters, and we're gonna extract the parameters of the function. I don't say it's the way that I would go in my application, but let's examine how we can use the parameters utility type. And we have to use only the first parameter, so we can access with 0. And as you can see, like data here, as you can see, description is required, title is required, type is optional. So everything works fine for us. Okay, so this was the example of manipulating the object. Maybe we use also the function manipulation utility as well. The third example is making the following code more easy to maintain. So we have like a big graph data structure that contains like lots of data, and we have the methods like render tool, render background, render nodes, and we do not use all of the inputs that we have in these methods. Maybe there will be like graph data without graph being fetched, and we still want to render some kind of accesses and container at the start. So we can make this functions work a little bit easier for us if we're missing some kind of data that is not required for these functions. So I will start by extracting maybe the axis type. So we have like the proper axis type everywhere, because this will be like our shape. In the future, maybe we will want to have like min max object, not the array. So let's have it like consistent through the application by extracting this. It's our code base. So let me see if there is like more of them. Okay, so it will be here. So yeah, maybe in the future, if we change how the axis type is defined, it will be easier for us to modify the code with it. Okay, so let's look at the getRender tool. We have the data, but we only use axis X, Y, and container. So here, potentially we will not have nodes and edges, and we would like to render this function. So let's go for picking what we need. So it will be axis X, Y, and we also need the container access. Okay, that's nice. And as you can see, we are returning some kind of context, like render tool is returning some kind of context that we are using inside our render background, render nodes, edges, functions. And maybe we want to have this like defined as a separate type, just to have it defined separately so we can adjust our function to it, not adjust the functions to the return type of the function. Really, this depends on how you would like to maintain your code. Here we're just playing around some kind of refactoring the code in the way that we maybe find it better. So let's say we create a render context type that is not gonna be a return type, but let's copy this and redefine it. So it will be axis, and this get coordinates is number returning number, of course. Yeah, so this is the render context, and now we are gonna force our render tool to return it, and let's reuse it also here and here. Okay. So maybe the render context will be always returned by the render tools. So we will not pick only like the parts of the get coordinates, but for render nodes and rendering the edges, I see that we only need parts of the graph data. So we can potentially go for picking only parts of the data. So data could be the nodes here, picking only the nodes. And this is all we need. All we need is like nodes data. And for the edges, we need nodes, but also I see that we need also edges. Oh yeah, of course we need edges to render edges, but also nodes to have the data about where the edge is coming from and to. So this is how we like not omit, but pick. Yeah, I used the wrong utility here. Yeah, so as I said, this would really, how we would implement these functions would really depend on how we are gonna use it, but we have the options to limit the inputs and use still the same like kind of big configuration type in all of the places and simply pick what we need from it. And the last example will be about the creation of the refunds function that is gonna handle every type of the items except wholesale. So let's assume that we have some kind of refund item that is can only accept new and used types and cannot accept wholesale. So we're gonna need the item that is gonna have the same, like everything except type, and the type will be limited to not include the wholesale. So this type would look something like this. So we are omitting now the type. So this is where we go for not for the pick by the omit. So we will always have, yeah, even if we add new keys to the bot item, it will be still like up to date. And for the type, we are gonna go for bot item type. Okay, this is the same, but we need to limit the wholesale. So here it will be the exclude utility used. So we exclude one of the options from the union, and we exclude wholesale. Okay, and as you see, even though our code is working properly, the TypeScript has sometimes problems with like limiting the parts of the objects. If you would extract it, so we would have like type and rest of the object, and we would go for this check, we would be able to use this one here without problems. So sometimes we need to help TypeScript a little bit with our code, but yeah, this example was mainly focused on using utilities. So here we have omit and exclude, and also we are using type lookup to have it also updated. So when it's gonna be new value, so this new value will be automatically added and the code will be automatically fine with our changes. So our refactoring will be changing only one line of the code. And this is where we are aiming, just to help us maintain our code with ease. And the utility types are helping us in achieving this goal. And the next part will be about the templates, which is also helping us to create a generic code that is used everywhere inside the code base and is always up to date. A significant aspect of software engineering involves constructing components that not only possess well-defined and consistent APIs, but also offer reusability. When we have some general logic that works with a wide family of similar data structures, we can use templates to create generic types. Generics are types that accept arguments. These arguments are other types. Like in functions, we use these past types to create a new result type. We should think about it as a template to generate more specific types, but with common shape and logic. Let's begin with the simplest example, a generic object that contains a value key capable of holding any type of data. We are trying to create a family of types, so we are not marking value key with any. Such a template can be utilized to generate similar types that are having the structure of the template, while we substitute every argument with the provided type. So when we are passing string type as t, we get the structure as an object with value, which is a string. Passing number, value key will be a number. If we pass a tuple, the value will be expected to be matching past tuple types. We aren't limited to just one argument passed to a template type. In the example, we have transform generic, which needs two argument types. As you can see, we can use these argument types for any part of the final type structure. It could be the value of an object's keys, or even the return type of a function. Like in functions, these arguments can be used anywhere inside type definition, which is the equivalent of function's body if we stick to this analogy. This is how we would use generic to create a string to number transformation object. We can create a reusable general type that will be specified in details for each use case. Let's consider an API response that can be either successful, returning some data, or an error with an error message. We can create a general API response shape. Notice that we are using in this example typeguard status key. Now, within our application, we can have various response types, but their structures will be standardized. This also means it will be simpler to write generic handlers. This subject will be explored in details in the next section about generic functions. So, for the login, we expect to receive email and username. TypeScript knows and shows tips about the response data structure. For reset password, we have another API response, but the standard is still there. We will get only different data type. We are expecting a token, and TypeScript is adjusting code to it. As you can see, we could consider creating a generic handler for our standardized API responses. This will be covered in the next chapter. I hope you see how this generalization makes it easier and faster to reuse common data structures. They will always appear inside our codebase. We can make a portion of generic type optional to define. Similar to function arguments, optional types cannot be followed by required ones. The difference here is that we must provide a default type. The syntax is visible on the screen. we created generic type template where the first argument is required and the second one is optional with default as string. So when using generic type template, when we do not provide a second argument, it will fall back to string. When we pass second type arg, it will be used as t value, so in the example, target key. Now let's look at an example with multiple optional arguments. Transform generic fun template has its all arguments optional. Notice that we can use it without brackets and it will be still a valid syntax. That would mean that all args are using the default types. So here it would be any to any. We can pass one argument, replacing only t type, or two. It will depend on our needs. Sometimes our templates are designed to accept specific types. We can constrain and limit arguments with extends keyword. Let's look how it's done. We create a template that will accept only arguments that are extending string. This could be useful, for example, if we were using this type as source of keys. Strings can be used as object keys, so this limitation would make sense. That means we can pass standard string there, but also specific union of string values. On the other hand, we cannot pass, let's say, number into this type. Another example shows how we can limit template arguments to only objects. We use extends object to do so. As you can see, we also provide an empty object type as default type. Notice that we can now safely use keyIn keyof t, as t will be some kind of object. This is why we sometimes want to create limitations on the arguments passed to templates. Often only some specific types will make sense to be passed. The next example showcases how we can force that a passed object type must contain a specific key and value. We are using extends name string. Inside template implementation, we can safely assume that name key will be present. Our template is replacing every key with a boolean value. See how the name key is ignored and instead changed into an array of strings. This is not really a real-world example, but shows how we can constrain arguments if needed. As you can see, the TypeScript will detect that pass type in the last line does not contain name string and reports an error. We also have an option to create relationships between arguments if the template accepts more than one. This is useful because quite often a template with multiple arguments needs to maintain a relationship between them to produce a valid result type. Starting with a basic use case. We can set the previous type as the default type for subsequent argument types. See how the default value behaves. If we pass only one argument to template, both t and s types will be the same. This transfers to the result type, so first and second keys. We are not limited to easy s equals t default value. With relationship template shows that we can use the first argument's type as a part of the default value of s type. Here it's a source of value key type. Examine closely the template result in the last example. Now let's see how we can combine these two mechanisms together. We will create a relationship between arguments and constrain one of them using extends keyword based on the other argument type. We are creating with extends template that accepts object as first argument and union of keys of that object. When used on the user type with name, surname, age keys, in the second argument, we need to provide union containing only these existing keys. That means that TypeScript will check our code and, for example, if during refactoring we would remove one of the keys, we will get errors if we do not remove their usage inside other places. In the previous example, there was one particularly interesting syntax that we need to cover inside this tutorial. P in key is TP syntax, creates a temporary P type of each of the keys inside K type. Using this specific P key when using TP type lookup allows to address the value type of the currently mapped key. Somewhat tempting would be using wrong syntax, key in K, T, K, but the K is a union of all possible keys of T object. The lookup type would return then union of all possible values of the keys, but not the specific key we are mapping. In the second example, we see that using this wrong syntax would give us completely unexpected type. Name and age would be string or number unions. When working with object remapping, and if you need to treat each key separately, always use this temporary key syntax to achieve desired results. Okay, let's look at one more example of relationship between arguments with constraints. We are creating a template that accepts the item I argument. The second data argument is required to contain an item key that is an array of I type. Using these templates looks like this. The item is a string, so the second argument is forced to have items as an array of strings. The second argument can be an object with additional keys, as it still matches constraints put inside template definition. See how the result type looks like. Up until this moment, every template we discussed was fairly straightforward. We got some type as a parameter and used it inside the return type. But in many cases, we will need to change the output if the type will be matching some specific condition. For this case, there is a special condition types syntax that we can use. The condition resembles ternary operator. Our check is inside the extends condition, and we can define type if it's true after the question mark, or otherwise fallback type after the colon. On the screen we have a basic condition. If the provided as type extends string, we are returning pass type as an array. Otherwise, we get object with value key of the type. So when we populate replace string template with a string, we get an array of strings. When we pass types that do not match the string condition, here it will be number and array, we get the object type with appropriate value key. Next, let's consider a more complex example. We will create a JSON serializer. This serializer creates an object containing serialize and deserialize methods. The use case. It will be a general way to serialize objects to strings and then deserialize them. While it works well for most data, it requires special handling for, let's say, date instances. Currently, we'll skip handling arrays as they require more advanced features. Bear in mind that the final result will be not a complete solution, but we will have a good example where to start with conditional types. We are creating a template called JSON deserializer. It will accept t-type as an argument. Let's start by checking if t is an array. We use t extend any array. For now, let's not allow arrays. They require some more advanced syntax that will be covered in advanced templates. For now, let's mark an array as unsupported by returning never if the condition is met. After getting rid of arrays, we can check if t is an object. We do so by checking t-extend object. The main focus of this task is to get familiar with conditions. The date is also an object, so now let's check for it. We are using t-extend date condition. JSON serializes date objects to ISO strings, so let's mark the value as string after the question mark. Okay, we handled the date object, but what is left for other objects? JSON will serialize each of their keys in the same way. We are using key and key of t syntax that was covered previously. Every key will be serialized using the same mechanism, so we can use JSON deserializer on each of the key types. This shows that we can create a self-referring templates, which is super useful for more complex scenarios like here. After we handle arrays and objects, we can go to the primitives. Let's check if the left value is string, number, boolean or null. If so, let's return it without modification. For all what's left, for example undefined, let's mark that our mechanism does not support it by returning never. Okay, this is a helper template, but what does the final object look like? We will create a serializer type that contains serialize and deserialize keys. Serialize is a function that can accept the base type and return serialized version. We are using JSON deserializer helper template for it. The deserialize method will be an opposite operation. Let's inspect our templates in action. First, we pass object with name and date keys. In the output type, we see that date got replaced with string, as it was expected to work. This is working also if the date key is nested deeper inside the structure. Notice that self-reference is working. User date key got replaced as a string as well. If we pass unsupported types, we will get never in our final type. This will prevent TypeScript from allowing creation of such objects, as they should not exist. This check is also working if the unsupported value is deeper inside the structure. The last example demonstrates how to detect an empty object. We use extends never check, which identifies type mismatches and adjusts the final type to resolve issues. So here we ask for t, which would be an object. If we use key of operation on the empty object, the result will be never. Here we are checking for this condition using key of t extends never inside ternary operation. In the output, we have a template into which we can pass object. If the object does not contain keys, the output is null. Otherwise, we do not change anything. The trick here is that key of empty object equals never. While these specific checks might be challenging to remember or conceive, the internet and community resources can provide solutions. Once properly written, most of these templates are rarely modified. In the upcoming chapter on advanced templates, we will explore more techniques used within these templates. If you feel overwhelmed, don't worry. We will become more familiar with extend syntax when covering generic functions. Defining generic templates is more abstract than adjusting return type based on the function's logic. We are ready to dive into the templates exercises. This one will be a little bit more challenging than the previous one, so don't hesitate to stop the video and try to solve the problems by yourself. I will go through them because I created them and solved them before recording this video. So yeah, it can take a little bit more time to solve these problems than the previous one. So as always, I will start by removing this XYZ unknown type. And the first example will be about the creation of the generic type that could represent the whole family of types. So here we have some kind of API responses. We see that the positive responses, like the proper responses, have status 200 with some kind of body which is different for each of the response. If we have the error response, we have like 400, 403. Well, of course, it can be much more generic, but I will stick with the examples that we have here. So I'm gonna create a generic response type that will have some kind of response object. Like it can be object, it can be string, whatever. So we'll have like two main statuses. The status key here behaves a little bit like a type guard with the number as the value. And for the successful responses, we'll have the body of the provided shape. And if we will make, if the API will return some kind of problems with the status of 400 or 403 for this, for now, we'll have the reason as a string to explain us what went wrong. So the user details response in this example would look probably something like this. So it will be response with this kind of data that we expect. Of course, now we have this option that, okay, the response can fail, but now we can create some kind of generic logic how to properly use this generic type of response all across the application. Our code will be consistent. We'll every time we'll need to adjust our code, we'll need to how to do it. So yeah, if we have kind of like generic template of the responses or the shapes of the functions that are used across all the application, we can use templates to reduce the boilerplate and have the consistent code everywhere. It will be much easier to maintain. So the second example is also about the creation of the generic family of the types. So let's see how these types look like. So we have some kind of object, and we are putting the input and output and having like a check function, which returns if the objects are the same. And if they are not, see that the same key is also like type guard for this one. We return the list of the keys that are different. So of course, for each of the type, this list will be different. The input and output will be different. So we can create a generic template. Let's call it like check template, which will be accepting one object type. So let's call it like D extends object, because we're gonna try to extract the object's keys. So let's force us to pass the objects here. And how does this template look like? So we have the input and output, which will be of type D. And we have a check function. The check function is also accepting A and B of type D. Okay, and what is the output? So the one part of the output is like always the same. So this is like the same is true. But when we have the same false, we can copy this. But of course, it will be not always the keys ID and username. So there will be an array of the keys of D. So we can use key of D to define it. So this is like a generic template. And now with this template, all we need to do to have like everything in the code set up in the same way, in the same manner, we can use this template to generate this kind of comparison objects. And as previously, if we would have some kind of generic function that could handle this kind of checking of the objects and their differences, it will be much easier to maintain. And this is much quicker to use than like copy pasting. If we have some kind of logic that is repeated across the application, we can go for templates. Okay, the third example is about adding the constraints to make the code safer. Okay, so we have the type that is returning the full name result. And how does it look like? Okay, so we know that the data needs to be containing the keys, name and surname. So we need to force that the T must contain these two kind of keys as the strings. So we can do this, of course, by forcing the extend the object that is containing this kind of keys. Of course, the result will be also following the same rules. And okay, we have a full name, which is a string, but we get the rest of the object. This is like omit T, name and surname. Even the TypeScript is really helping us to solve these problems. So this is the proper definition of the return type. So we take a T object that is needed to contain this kind of keys. Then we replace them with full name, and we are getting rid of name and surname because they will be no longer in this object after the function call. So yeah, this is how we can add some kind of constraints to the input. Okay, so the fourth example is about like trying to understand what the template is really doing, because this one, I don't see like any practical usage of this one, but it's like crazy, and maybe we can inspect what is happening here. So this is the template that we pass two types, and in the return we have a type that is telling us which kind of keys are in the first and the second object at the same time. And the miss part is telling which keys are not present in the second one, but are present in the first one. And okay, we maybe understand how it works, but maybe it will be easier for us to understand when we simply play around with the template. Sometimes the best way to understand how it works, simply play around with the templates. So we have the key, the object with the name, and the empty object. So the result is like this. So we do not have any keys that are in the both objects. And in the second object, there is no name key. So then miss will be containing name. Here we have the opposite. And matching, there are no keys that are in both first and the second object. And there is also no missing keys because the first object does not have any keys. Here we have matching name because name is in the first and the second, and we miss value from the first because it's not in the second. And when we reverse it, we will have matching name as was previously, but the miss will be with the never because we are not having any new keys in the first object. As I said, sometimes it's hard to understand how exactly the template works. It's easier to inspect it and play around with a few examples just to understand how it works. So the fifth example will be more practical. So we're going to use the ternary expression to create a template, and let's go step by step. It should accept only types. Let's add extend object. Okay. And we're going through each of the key of this object. So let's start with our like standard approach to the keys. So P in key of T. Okay, and what we have next. If the key is a string, we'll convert it to an object with the same key and string. So the check will be TP extends string. Okay, and here we need to create an object that will have this key and the values will be string. To do so, I am using record here because I don't know if we can like use it, create the same logic with some other tools that are built in this TypeScript, but I think the record is the proper solution for this point that we want to achieve. Okay. If the key value is an object, return the same logic recursively. But we want to keep arrays intact. Because the arrays in some ways are the object, let's check for the arrays first. Probably we should have switched the steps, but we must remember about this. So let's go for the arrays check first. So to check if TP is an array, we're gonna go with TP extends any array. If it does, we are not modifying it. Let's go for this current value. But if it's not an array, we check if it's an object. Okay, so to check if it's an object, it will be TP extends object. Okay, so if we have an object, we run the same logic recursively. So as was told before on the presentation, we can refer the template inside itself. So let's run the template on itself. And for whatever is left, let's return what was there. So as you see, we practice a lot the ternary expressions, and now we are good to go to inspect the results. So we have a type A, which is a name string. So we are in this, if the key value is a string, we'll convert it to an object with the same name key as a string. So we should be name string. And when we use the IDE, it's not really so helpful for us. because the definition is so complex. But we can play around with by faking the object. So I'm creating some kind of fake object, and let's play around. So there will be name, and there will be name inside the name. It will be a string. So we're good to go. With the type B, we should have age and array containing name. So I'm using the same technique. Sometimes I'm using this just if I'm not sure about the structure of the object. So okay, age is a number, array is an array of the name of the string. So as expected, we're good to go. And the final check, we have like the nested structures. So the child should contain surname, and others should be other. Okay, so again, we're gonna fake it and let's inspect. So inside the parent, we have a child which have surname. Great. And the last check is that other is a string. So it seems that our template is working as intended. Okay, so the next part will be the generic functions, where we'll work on the templates inside the functions, and it will be much easier to understand because we're gonna get rid of this general thinking about the templates and go for simple implementation. We are familiar with creating templates that can describe families of similar types. For now, we focus on the syntax and options, but less on practical examples. We are going to gain knowledge when working with general functions. They can accept a wide range of input data and return a corresponding type based on the arguments. Starting with the syntax, the example shows a basic identity function that logs input data. The syntax is identical to standard functions, but we add t as a template type argument. Rules for these arguments are the same as for type templates. We can assign default values, add multiple arguments, constrain arguments based on others, etc. We could implement the generic function marking input data as any, but we would lose information about the types. Let's look how naive generic would work for us. When we call the wrong function with the object as an argument, the result is any. We are missing input type data. So we can then execute code that does not really make sense, and we will not get TS errors or warnings. That's why we should use generic functions in such parts of the code and keep type information, even if the functions could accept any possible input data. There is also a way to define generic functions for arrow, lambda syntax. However, there is one problem with this syntax. In TS6 files, the syntax will be marked as invalid. The same happens for using casting instead of as. Hence, we are going to use function syntax for generic functions from now on. But the lambda syntax is still valid. For example, in Node.js apps, you can see this kind of code and should not be surprised. There is an interesting feature for generic functions. If possible, TypeScript will infer template types based on the input passed to the function. That means we can occasionally skip the definition of types. We have the same identity function from the last example. When called with hello string, the output is automatically marked as hello value. We can always define the argument by ourselves. Here we mark it as a more general string, and the x constant will be treated as string from now on. If we would mark it with a number and try to pass a hello string, we would receive an error. The example with identity function was a simple problem that could nicely demonstrate how a generic function works. We were able to skip definition of the return type, and TypeScript would deduce the result type based on the code. However, generic functions are rarely so simple. Sometimes we need to use any and as if TypeScript is unable to deduce the general type of the value inside complex and abstract code. Additionally, defining a return type is necessary to provide clear type hints for the final users. Let's start with something really easy. We will create a function that will accept any kind of input. If it's a number, it will be converted to a string. This is the implementation of this logic. We check if the input is a number and return string. Otherwise, we return input without modifications. Now, let's use it and pass different arguments. Passing text, we receive string. It's okay. When passing an object, we receive string or object union. And with number, we get string or number union. This is not how the function should work. The output is too generic. We can do much better. We notice that the TypeScript is struggling even with such straightforward code. The inferred return type is by default union of string and t, so it does not consider how the code actually works. We need to do manual definition of the return type. Here's a fixed version. Notice that JS final code is not changed. We are adding only specific additional type information. We are forced to add asAny to resolve an error that says that the string is not assignable to type t extent number, etc., etc., even though a string is expected to be returned for number inputs. TypeScript was not able to deduce that we are implementing proper code and force us to use asAny workaround. This will happen quite often inside generic functions. Now, after the fixing, we have passing text. The return is text string value. Passing object returns valid object type. Passing number, finally, we get the string as it was intended. We have another example for return type definition. We want to create a function that can accept an object. If the keys value will be a string, the function should split the text by the space. Below, we have a basic implementation that iterates through keys and builds the result object. The initial implementation is functional, but the return type is an empty object inferred from the initial type of the result variable. Let's fix the function to return the proper type. First, we create a template helper type that is defining what the outcome type of the function should be. We are using p in key of t syntax followed with extend string conditional check for string keys. After we have a template which defines the output of the generic function, we can use it as a return type. The last part is to mark the result variable inside the function body to be of this type. We are using as casting. Let's see how it works. We are passing an object with name string key and age number key. The output type is name array of string and age key is not modified. Works as intended. We created a helper template to reduce code duplication. We could potentially mark result variable with any. If we make a mistake inside the generic function, TypeScript will not detect the problem. Therefore, when dealing with generic functions, we must be extremely careful in their implementation. We rely on the deduce return type, so making a mistake in such a function could be detrimental to the type system not catching errors. Personally, I would advise always covering such functions with unit tests. Ensure that TypeScript checks input and output types within the test files. Now we are ready to implement a few generic functions. We have a few exercises created for this part of the tutorial. And as I mentioned, it's really important to test these kind of functions with the unit test because we're gonna use as and we're gonna help the TypeScript with the proper typing because some of the functions will be too complex for him to analyze. And because of this, we want to test our exercises with the unit tests. So I created the unit test for each of the exercise. And because they are not implemented, the TypeScript would complain and we would be not able to execute them properly. So let's start by commenting the code that is not implemented yet. The same for the imports and the unit tests that we're not having implemented yet. And then we will see, we're gonna implement the first exercise and see how to execute the unit tests and check if they are working properly. So the first exercise is pretty easy. We want to have a promise of the passed value to the function. So let's start with the typing. We are not limited to the type of the input value, so it's gonna be like generic t. The value will be also of a t. And to implement this function, all we need to do is return the promise resolve of the value. And maybe one interesting part is how we would try to implement the response type. So the naive approach would be, okay, it will be a promise of t, but what will happen when we're gonna pass a promise here? So we're testing it. We're passing a promise that should resolve to the null. And let's see how the TypeScript understands it now. Okay, so it's assuming it's a promise of a promise. It doesn't really make sense. So let's see how the resolve function is handling it. So it's using this kind of awaited utility that checks if it's a promise and then provides the value that it should resolve to. Otherwise, it is wrapping with the promise. So this is the proper return type of this kind of function. But for this exercise, we don't need it. Like the TypeScript is doing it all right without our help. It's detecting the proper return type, and when we expect it, it's a promise of null, which is the value that we're expecting in the first place. So we have our exercise implemented. It was easy, and let's use our tests to see if we did it properly. So we're gonna use the command that we have here in the exercises description, and let's execute the tests. We're gonna run the test for the first exercise, and yeah, the test passed, so we implemented the exercise in the proper way. We're good to go with the another one. So for the exercise number 2, we want to create the generic functions that will send emails. The function will accept the template and accept the data and the recipients, and we should use the template that sent email values from the external library mock file. Okay, so let's inspect how they look like. So the first thing that we need to notice is that the template is limited to accept only objects. So this will be some kind of like constraint for our generic function. And the template is a function that accepts the same data that we provide as the input of the template and returns string. So we can use the template to generate the text that's gonna be used to send this fake email. So the recipient is the string. So this will be like a list of emails probably. So I think we are good to implement the types, like the general type of our function. So the function will accept some kind of data that is extending the object. And we need to provide the template to generate the content of the email, provide then the data that the template is like needing to generate the text, and the list of recipients. So it will be like an emails list of strings. And now we are good to send the emails to each of the recipients. So let's go with mapping all of the recipients to send the email to it. Okay, so we're sending the email, the recipient, we have the recipient from the list, and we need the text. So we can use the template and pass the data to it. And okay, so we have the list of like the promises that should indicate sending the email. And we want to return the message IDs. So, okay, we have the list of promise. So how can we resolve it? So we're gonna use the promise all utility. And now with this wrapper, we're gonna get like the promise of string array, and we can simply return it because this is what we need. This will be like a list of IDs. And maybe to make the function a little bit more transparent, I will mark it as an async function, and I will await the promise here to have like the better stacking of the errors if there will be some kind of problem inside the send email promise. Yeah, we're good to go, and we're good to test if we implemented our exercise properly. So let's uncomment the import, let's uncomment the test, and let's run tests. Everything's green, and we can go to the next one. In the third example, we want to have a function that will accept the list of items and use a mapper that will map it to the other type of items. So this is the example where we can create like the generic function with 2 arguments. So that will be like the t, which will indicate the items, and the mapper will be a function that converts the item of type t into return type. And how we can map it? We're basically like creating the function that is already in the JavaScript, is like the map. But yeah, the exercise is an exercise. And the TypeScript can detect by itself it's that the return type is like the array of R type, but we can like provide it for more transparency. Yep, and let's test this. Let's uncomment the import and the tests, and let's run tests again. Okay. Going to the fourth example. The fourth example is a little bit more complex from the previous one. We are gonna create a generic function that will compare 2 objects of the same shape. So just starting, we know the input arguments will be some kind of object type, and we're gonna accept 2 objects of the same type. And what is the expected result? Okay, so we want to have like this object general like comparison. So we're gonna have like the common part, we're gonna have the added part. This is the part that is inside the object B, but not inside object A. We're gonna have like deleted part, so the part of the object that is inside A but not inside B, and the modified part where we're gonna have like the previous from A and next from the B values. So let's try to implement like the show what is the expected return type. So starting with the common, added and deleted, like we cannot be sure what kind of values will be there. So we know it will be, in general, it can be either the whole object or the parts of the object. So we are expecting partial t here for common, added and deleted. And for modified, we need to go through each of the keys, and of course the objects can be the same, so it can be also the empty object, so it will be a partial object, but we need to go through every key and map it. So we're gonna use this technique that we use a lot, so p in key of t, and what would be the final output? Okay, so we have the object of pref and next. The pref will be of the same type, so it will be tp, and the next value will be of the same type, but of course the different values. Okay, so the TypeScript is now complaining because we are not returning anything from our function. So let's mark it that we're gonna return something, and let's start our implementation. I will just say that of course this implementation will be not the most like optimal one. It will be like the easiest one just for the example, because here we are focusing on the generic functions typing, not really their strict implementation. So we have this one condition that we should treat the undefined values as missing keys. So it will be easier for us just to go through the code with this. So I will start with getting the A object keys and B object keys. So A keys is the object keys of A, And because this is like a generic object, we're gonna have like, okay, it's a string array, but we here are a little bit more like, we know a little bit more than the TypeScript. Let's say it's the array of key of t. It will be easier for us to work with this, and yeah. And let's implement this kind of filtering to remove the keys that the values are undefined. So just for us to be able to work with it easy. So we're gonna remove keys that the a key is undefined. So the keys cannot be undefined with the value. And we're gonna use the same logic for b keys. So object keys of b, and let's filter it out again. Now we need to find the common keys. So the values will be the same in a and b. So common keys will be, I can go with the a keys, filter key, so a key equals b key. Okay, so this is the fastest way to implement this. Added keys. So added keys will be the keys that are present in b keys, but not present in a keys. So to do it, I can go with like, of course, the filter, and will be the b key, so that the a keys do not include this key. So we need to not include this. So we're gonna go with the same logic for deleted keys. So it will be, in this case, a keys that the b keys do not include. And how can we get the modified keys? I think we can go with a keys and simply remove all the keys that are common or deleted. And what's left will be modified. So yeah, let's go this way. So it will be common keys. It cannot be a common key. And it cannot be a deleted key. And now to generate these partial objects, we're gonna use object reduce for it. So I will go with the common keys at first. So the common keys, I'm gonna reduce them. So let's use the return type of the reduce. So it will be easier for us to work with this. Okay, so it will be a result key. Yeah. And we need to provide the initial value. Okay, so to implement it, we're gonna use the reduced version, and for each key that we are reducing, because it's a common key, we can access the value from either A or B. It will be no difference because these values are the same. Okay, to create the added partial object, we're gonna iterate, like we're gonna reduce added keys, and the added keys are, their values are from the B keys. So we need to provide the B key here. Okay, so the same logic, but in reverse, will be for deleted. So we're gonna reduce the deleted keys, and the deleted keys values are from the A key, and modified keys. Let's go for the modified keys. Okay, so this is the outcome. So we're gonna use it so the TypeScript will know that we are reducing to the proper output. And as you can see, the TypeScript is not complaining here, but we know this logic doesn't make sense. We need to have this kind of shape of the object. And that's why we need unit tests. The TypeScript will be not able to detect if our code makes sense in such an like extreme complex examples. We can make mistakes here, and we have the unit test so we can detect them. So yeah, I really appreciate having unit tests for this kind of generic functions in my code base, because they make life easier. So okay, we implemented this, and let's see if we did it properly. So I'm gonna uncomment the import, and I'm gonna proceed with the tests. And fingers crossed, they will be successful. Everything's green. We are good to go to the last example. And the last example is even more challenging. So we need to understand the idea. We are going to try to create a function that will represent the state machine. So this will be the shape of our state machine. So the state machine is going to have the keys that will indicate the states. And some states, we're going to need some kind of data to move to the state. For other states, we're going to need to just move there, providing no data there. And we would like to have this kind of implementation to have this move function that would accept this kind of specific object shape. As you can see, the step value is like a guard. So we're going to use the guard to make the code working properly for us. And there is going to be also a function that will return the state. So this is the input type. This is like describing the shape of the state machine. But now we're going to need to create the type that will represent the state of the machine. And then we can move move to the state and maybe they get the state that we're expecting. So let's play around with this idea. So let's copy this type and let's try to create some kind of similar structure to this step values and data values. Let's try to create something similar. So maybe we can start with mapping the let's create like helper template that will accept some kind of object. Okay, and we have the object as an input, so we want to iterate through it. Let's iterate through it and try to detect the empty objects, because these states we will not have the data to move inside the state. So let's try to detect them. So we're gonna use the p in key of t as standard, and let's detect this kind of empty object. So we had this magic snippet, some kind of things that you can working with TypeScript, we are gonna learn a lot of tricks how to detect different things. So we know that we can detect an empty object by using key of the value. So here the value is the value of this specific key, and key of TP when it extends never, we know this is the empty object. Okay, so when it's the empty object, we want to have the step, simply a step. So, okay, we want then, maybe I will go with the new line. Then we want to have simply the step. And the step will be of course, type P, because this is the step here. But what when we have the data? So we're gonna have some kind of keys that will represent the data that we want to go into the state with this kind of data into this specific state. So yeah, we have the data. So let's create this kind of thing. So in the alternative solution, when we have data, so we're gonna have the step value, but we're gonna need the data as well. And the data is the shape of the data that is inside the state machine. So okay, we have this helper template, and let's see what kind of output we have when we call the test type. Let's use the helper template and let's provide our state machine there. So yeah, so this is starting to look familiar. We have the init nicely, the loading. Okay, so these values are the possible, let's say, arguments for moving from and out of the state. So we need to simply access now the values of this kind of object. And to do this, we're gonna use the lookup, and we're gonna use the lookup of all of the keys. So we're gonna use the key of T here, and let's see. It's looking like we created a union that is describing the possible states of our state machine. So we're gonna use this helper template to do it. So we have it defined. Now we need to provide some kind of T extends object. So this type will be the state machine shape that we're gonna provide to the exercise. So yeah, we need to check if it extends an object. So initial state will be of the state of the state machine. So we can use our helper template and we get our initial state. So now what is left? We need to create two functions, getState and moveFunction. Okay. So we're gonna create a internal state. And we're gonna create two functions. So we're gonna create a function getState. And this function is simply returning our internal state. And we have the function move, new state. And the new state is also the helper, like we're gonna use the helper. And what it'll gonna do is gonna replace our state with the new state. Okay, and let's see if our implementation is correct. So the main problem here was how to create this state type based on the general shape of the state machine. So I hope you understand the idea behind this helper template that we can reuse inside it. And let's see if we did it correctly, because this is what's the most important. Our code can be green for TypeScript, but can work in the manner that's not correct. So we have the unit test that should check it, and our example is working. So for now, we can assume that everything is all right. Okay, I hope at least that the generic functions were a little more exciting than the previous examples. In pure JavaScript, working with classes used to be a real challenge. After the introduction of class keyword in ES 2015, dev experience got much better. TypeScript fully supports it and adds extra type safety to the basic JS syntax. The creation of the class is the same as in standard JavaScript. We use the class keyword to do so. We can define properties inside TypeScript by declaring the property and its value type. However, the code you see will produce an error if we are using strict mode. We are referring to strict property initialization. It is highly recommended to use this mode. Therefore, when creating classes with required properties, we should add their initial values or initialize them inside the constructor. An additional note: the field needs to be initialized in the constructor itself. TypeScript does not analyze methods invoked from the constructor. Read-only properties can be defined with the read-only prefix. This will prevent assignments to the field outside the constructor, but the check is only at the type system level. We can add methods to our classes in the same way as in JavaScript. Inside them, we will have access to properties, etc. Here we have a rectangle class. We are adding getArea method, which calculates area of the rectangle. We can use this method on the instance of this class as shown in the example. Similarly, we can add getters. Setters will follow the same rules. We are changing the getArea method from the previous example into getter. we need to add the get keyword. The TypeScript will infer the return type as getter's type. When accessing it from the instance of the rectangle class, we will receive a number. The concept of generics has already been introduced. The same mechanism that we saw for the functions applies here. When creating a class, we add template parameters. It works like inside generic functions. We can access and use this template argument type anywhere inside class definition. There is one small exception. Inside static methods, we cannot use pass type arguments. The example you see is just a general demonstration of the usage of generic class, so don't pay attention to the details as it's only an code example. A class can be forced to implement an interface or corresponding object type by using the implements keyword within the class definition. Let's create an interface that we want to implement. We have a withArea interface that has one method. When creating a rectangle class, we mark it as implementing a previously created interface. If we remove getArea method, the TypeScript will complain about the missing method. TypeScript checks whether your class instance matches the required object shape. However, it does not add any additional context to the interface. Therefore, we must, for example, specify the types of arguments within the interface's function definition. If we do not do this, we will have an invalid implementation. Let's investigate our example to understand how it works. We are creating method that is required by the interface, but we are skipping check circumference value argument type. It should be a number, but as mentioned, the TypeScript is not adding this context to the class implementation. It's not complaining, as the currently implemented method is of type value any into boolean, so it can accept number as required by the interface. Let's fix it so we get a safer code. The correct implementation should copy the function definition. We implement the interface properly by marking value as a number. Now TS will detect that we made a mistake inside our implementation. It's also possible to implement multiple interfaces simultaneously. We separate them after the implements keyword using commas. We saw in the basic example how and when we need to define a constructor. We can also use the overloads mechanism and declare multiple shapes of the constructor. Inside JavaScript, there is no overload mechanism. This is only a TS feature that allows defining multiple different shapes of the possible arguments combination. That's why we can only implement once, so our code should consider different types of input data. As always, we will use an example to explain it in details. We are creating a point class. We want to have two ways of creating an instance. One would be passing two number arguments for x and y coordinate. The second one is a string, which will be parsed to extract coordinates. We define these two different shapes of expected arguments. Now we need to have one implementation which will adjust its logic to the passed arguments types. We are creating the third constructor, but now with the logic inside. This one will be not taken in consideration as a valid constructor by the TypeScript. Only the previous two will be considered and shown as tips inside your IDE. The implementation of the general constructor must handle all possible different overloads. Here we define it as XS unknown and optional Y unknown. Inside code, we adjust logic to match both ways that the constructor should be called with. So we are checking for string and parsing it, or treating the XS and Y as numbers instead. If we would have more overloads, the logic would have to be adjusted for each of them. Overloads can also be defined for standard methods. We are creating the move method that will have similar logic as the constructor from the previous example. We have two different ways of calling this method. We create a general third one that is handling all input options. The mechanism is working as previously. In contrast to the constructor, we can also define overloads on the interface that the class would implement. Here we have the withMove interface that defines two ways that the move method can be called. If we extend our point class, we would need to define this method like we saw in the previous code snippet. The mechanism of inheritance remains the same as in standard JavaScript. Here we will focus on how this mechanism interacts with our type system. For a more in-depth understanding of how inheritance works, you should refer to some JavaScript tutorial that covers classes topics. TypeScript uses the extends keyword in the same way as JavaScript to indicate that the class is extending another class. Let's examine this example. We have an animal class that has a move method. We are extending the base class to create a dog class. This class has a new method called woof. When we create a dog instance, we can use both methods. One will come from the base class, the second one will be from the derived class in this case. We can always override a method present in the base class. Here we do it for the move method from the animal class. As you can see, inside the dog class we make our method more complex by adding an argument to it. For type safety, we are forced to accept this argument as optional to cover contract defined by the base class. This is where TypeScript type checking appears. Remember that even if we allow no argument passed, the function will be triggered from the overridden method. Sometimes derived classes have properties with a more strict type than those in the base class. In the derived class, we can specify that X is more strict, but we cannot make it more generic, as TypeScript ensures that our derived class follows the base class contract. There is a potential problem with the above implementation. It becomes visible when we use define for class fields true in the TypeScript compilation configuration. Let's examine this code example. We have a base class with X property, which is an optional number or string. In the derived class, we define that property is an optional number. Everything seems fine, but let's inspect how this code will be compiled into ECMAScript compilant code. In the derived class, there is a second object-defined property call for the X property. This would clean up the X value set inside the base class constructor. The code in the derived constructor will override X property from base. If this is intentional, we should add an initializer. In our example, to avoid this issue, we should use the declare syntax, designed to overcome the problem of restricting properties without reinitializing them. Using declare in such cases will ensure it works properly in every possible scenario. We can access base class methods using the super keyword, which functions the same way it does in JavaScript. TypeScript ensures only that we pass proper values to the base methods. We created a rectangle class with getters, setters, getInfo method, and a constructor. We also created a square class, which extends rectangle class. We can use super methods for constructor and getInfo. We can also utilize super inside setters and getters. A note to consider about this example. When overriding setters, getters, we must define the corresponding getters, setters as well. Otherwise, they will get deleted. They are defined together under the hood. JavaScript is not the most intuitive object-oriented programming language, and while TypeScript makes it safer to work with, it doesn't eliminate all language-specific so-called features. But all in all, TypeScript adds additional safety layer and makes working with classes much better. Okay, let's go with the examples and the exercises for the classes. And we're gonna go with the first one. So the first exercise is about the implementation of the point class, and let's go step by step. It should have X and Y properties. As it's a point, it will be numbers for us. Okay, the TypeScript is complaining, but the second step should fix it. The values should be initialized inside the constructor. So let's force us to provide some kind of data to the constructor. And of course, we need to populate the properties with the data from the, we need to initialize them. So now the TypeScript is not complaining, everything is good. The third part is it should have a method that returns a quadrant. Okay, so let's implement this getQuadrant method, and maybe we can indicate what kind of output is expected, because it's not gonna be like a string but a specific values. And this logic is gonna be like really basic one. I'm not even really sure if it will be like the 100% accurate one, but let's go for some kind of implementation for this tutorial. So it will be the first quadrant. So if the y value is greater than 0, then what is left is that we are in the second quadrant. And if this x is smaller than 0, let's go like this. Return is like the third one. In other cases, return fourth. Okay, so this method is implemented, and let's go with the getter. So we need to create a distance from the 0, 0 point. So it will be a getter, so we're gonna return math, so it will be a square root. And I'm gonna like multiply this x by this x and add this y times this y. Okay, so I think we implemented everything that we wanted for the first exercise. The TypeScript is now complaining. So let's go to the second one. We want to add interfaces to the class and implement them. So let's mark that the person class is implementing with full name and with mature check. Of course, now the TypeScript is saying, but you are not implementing it. So let's implement it. So as you can see, the IDE is helping me to do it. The full name, it's not gonna be a property, it's gonna be a getter, because we have like the name and surname. We can build this full name of the person. And I'm gonna do it with the string literal. This name, and let's add this surname. Okay, so we implemented the first, and let's implement also the isAdult method. Of course, not here, but here. Okay, this adult method, and we, as I was telling in the theoretical part, we need to like copy the implementation to provide the proper types. So in my country, you are adult when you are 18, so I will use it as a default value, and I will simply check if our age is greater and equal than regulation age. And we implemented also the second interface, and we're done with this exercise. The third exercise is about the implementation of a class that should represent a DOM selector. So it should be initialized either by providing the ID, so this is this basic initialization, or by providing the configuration. Okay, so this is the second way to initialize. So as you can see, this is gonna be the overloads for the constructor. The class should have a method returning a specific DOM element. We can use DOM query selector for this example. Okay, we can initialize the query inside the constructor and use it. Okay, and we also see this class is gonna be like a generic class, but we'll implement it like in the next step. So first, let's define what kind of shapes of constructors are we expecting. So the first one is easy. It's gonna be ID, which is gonna be a string. The second constructor is more complex. So maybe I will use this and create some kind of helper type. So let's call it selector config. And of course, it's gonna be string, and the value is gonna be also a string. So we're gonna have either the ID or config with the selector config. Okay, so now we need to create this like generic constructor that will handle both cases. So we know we're gonna get either the string or the selector config, and we need to initialize our DOM selector. So as was suggested here, we can create like the query inside. So let's create a query that's gonna be a string, and let's initialize this query based on the inputs. So if type of x equals string, it's easier to detect the string, so we're gonna go with this one. Yeah, this query is gonna be, so the query that we have for the ID is simply hash ID. Else, okay, else, in the else branch we know it's gonna be a config. This query, so we need like the query for the data. So the query will be something like data key equals, and the value will be, oh, sorry, the equals should be here, x value. Okay, so we created the selector, and now all that's left, we want to have this get element method. So as suggested, we can use the document query selector for it. So let's go with the query selector. We're gonna use the query that we created in the constructor. And the first part is good, but as we can see, we want to have like it more generic. So our class should be a little bit more generic. So the base thing is an element. So the E extends element. And now we want to use this E as the base of query selector value. And yeah, the query selector is now E or null. And do we have value of never exists? Yeah, because we are not returning. Now, after returning the value of the query selector, everything is fine. Okay, so we remove all the errors, so I think we can go to the last example. And the last example is about the inheritance. We want to implement the missing parts of the code, and the manager and developer classes should inherit from employee. So let's start with the manager, and let's say that this class extends employee. As you can see, we are getting warnings that we did not call the super, and let's call the constructor. So let's pass name, and for the role we can go here, that's a manager. Of course, the TypeScript is also warning us that we forgot to initialize the property. So let's fix it. Let's provide the initial value. Okay, so get details. Okay, so the output is from the base class, and we add some kind of additional info. So let's uncomment it. So let's use the get details from the base class. So we're gonna use super and get details. And here we're gonna use the property, which is like unique for the manager, so number of teams. For the developer, we're gonna go with the same things. So we're gonna say it's extending an employee. We're gonna fix the problem with no initialization. Here it will be a developer, and we're gonna provide the value like initialize tech stack. Okay, so get details for the developer. I see that for the tech stack, we're listing it with the comma separation. So we're gonna use the base get details method, and then we're gonna use our internal tech stack and display it by joining the list by the comma. And that's all. We implemented the last example for the classes. I'm really glad that you made through the whole second part of the tutorial. The third part of the tutorial will be focusing on the advanced topics. We'll cover complex templates, rarely used class features, and general setup of the TypeScript application. These tutorials takes dozens of hours to create, so if you found the knowledge useful, please consider liking the video and subscribing to the channel. All the materials are, as always, in the description. See you in the final part of this tutorial.